Yeah, I think I'm recording. It's my first attempt at this, guys. Um, so I wanted to talk about comparisons of improper integrals today. Have you guys watch me talk about this for a few minutes before you work on your own? So the idea here is that these are integrals that we're not going to want to evaluate directly, but we're going to want to compare them to easier integrals to see if they converge or diverge. So let's look at these two examples. Integral of 1 over x squared plus 1 and the integral of 1 over x squared minus 1 from 1 to infinity. Notice the 2 right here. Why is that 2 to infinity instead of 1 to infinity? Well, if we plug in x equals 1 here is bad, right? So I'm just avoiding that. That would be a vertical asymptote. This would be improper at both endpoints if the integral started at 1. And so I don't want to think about that. So I just want to think about what happens as x is going to infinity. So just move the left-hand endpoint over to 2, so we don't have to worry about that. Okay, so the first thing is this idea of in behavior. So there's this informal approach. And that's basically what happens as x gets large. And the way we should think about this with this example is that here, when x gets large, adding a plus 1 or a minus 1 doesn't really affect the size, kind of at least like as a percentage of the size, right? Like a million squared plus 1 is pretty close to a million squared. So at least as a percentage. I mean, it's off by 1, no matter what x is, but we want to think of the plus 1 or the minus 1 as being sort of negligible. Maybe I'll write that plus 1, minus 1. Negligible in this case. Okay. And so we kind of want to just pretend it's not there. And if it's not there, we get the much simpler integral, integral 1 infinity 1 over x squared, which we know converges, right? This is the p-test with p equals 2. And so this informal idea is that, well, okay, if these two integrals kind of have the same, if these two functions, sorry, have the same sort of in behavior, then the integrals should either both converge or both diverge, or all three should converge or all three should diverge. And since the simplest one converges, then the other two should converge as well. Okay. All right. Now, there is a more formal approach, which I will want you guys to be able to write out. And that's to actually set up some inequalities, use some limits. And this is kind of the more like formal approach. So inequalities and limits. So if we just go back to this guy right here, I'm claiming this one is actually pretty easy. So you can write an inequality right away, right? X squared is certainly always less than x squared plus 1. It's always greater than 0. The greater than 0, I mean, it actually turns out to be sort of important, but the main thing is the x squared less than x squared plus 1. So then if we flip them over, if we take the reciprocals, right, of these, then what happens to the inequalities? Well, they all flip, right? So, right, like 2 is less than 3, and 1/2 is greater than 1/3. So when you flip the thing over, you actually, when you take the reciprocals of the numbers, you flip the inequality from a less than to a greater than. It looks like a greater than or equal to, so I'm not gonna leave that there. Okay, so that's true. 1 over x squared is bigger than 1 over x squared plus 1. And then if we integrate both functions from 1 to b, so remember when we do improper integrals, we always have this finite, right, endpoint b that we're going to eventually want to let go to infinity. So we just go from 1 to b here, and we integrate, but since the functions are related that way, then the inequality also is still going to hold, right? I actually switched the order here. Just, I don't know why. X squared plus 1 is the one we care about, and it's less than the integral of 1 over x squared. from 1 to b for any b, doesn't matter what the right-hand endpoint b is. And, you know, you can see this, by the way, if you just think, maybe I should draw a picture over here. If that's 1 and that's b, pretend b some large number, we know 1 over x squared is higher. So that could be like 1 over x squared, and then 1 over x squared plus 1 is smaller. So maybe it's down here. And the point is, since, yeah, if that's 1 over x squared plus 1 is the purple one, the blue one is 1 over x squared, then the area under the purple, which is what is right here, right, is represented by this expression. And that's less than the area under the blue curve right there, which is represented by this expression. Okay, so you guys know what's going on. You can see it visually, you can see it algebraically. And then if we just take the limit, so now we go down here and we take the limit as b goes to infinity. So we take, you know, from here to here, we take the limit of both sides. And it turns out that inequalities are sort of preserved by limits. To be honest, if it's a real general situation, there could be a less than or equal to here instead of just a less than in a general situation. But here, since there's actually a discrepancy in the areas, it's actually still a strictly less than, but we could just say less than or equal to if we wanted to be a little more careful. And we take the limit of both sides, and that still holds, and taking the limit of both sides just gives us the actual improper integral with the infinity on top, right? That's kind of the definition. Okay, good. So, so we know this is the more formal justification that basically this is finite right here. This integral is finite, and this is smaller, but it's positive. I mean, I could put a greater than or 0 here. We're integrating a positive function. And so it's trapped between two finite numbers. It's trapped between 0 and whatever finite number the integral of 1 over x squared is. So this also must be finite. So also finite. And that's how you use the inequality to make the justification. Since so we just showed that this integral that we cared about, the integral of 1 over x squared plus 1, is actually finite. So it converges. Okay. That's all great and well and good. Hopefully you guys are still with me. By the way, just a general comment, it's a good idea to like pause, think about stuff on your own, write out some of the details for yourself. You know, that's the nice thing about these being recorded, is that you can sort of go through them at your own pace. But I really do expect you guys to be using pen and paper and basically writing this stuff out for yourself. I think that's probably the best way to take notes from this. Okay, so let's move on to the other version where it's x squared minus 1 instead of x squared plus 1. And I claim the argument doesn't work. The same argument I just gave does not work. It does not help us, which is kind of annoying. But it's salvageable, and I'll show you how to salvage it in a moment. But yeah, so here we're looking at the minus 1. And so before we had x squared plus 1 was greater than x squared, right? Or is that how I had it? Let's go back. Yeah, x squared plus 1 was greater than x squared. And so now we have x squared minus 1 is less than x squared. And so basically, if you track through this entire argument again, you know, this inequality right here would flip. 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 And you'd end up with basically this inequality right there. That integral 1 over x squared minus 1 is actually bigger than the integral 1 over x squared. And now if we try to make the same conclusion, I mean, this is the problem. The inequality goes sort of quote unquote the wrong way. This is finite. And now this guy is just bigger. But bigger than finite, well, it could be another finite number, right? Bigger than 1,000 could be any finite number, but it could also be infinite. be finite or infinite. And so in that case, we actually haven't learned anything about this integral by making this comparison, by making the simple comparison of x squared minus 1 being less than x squared. And so that's super annoying. And so I'll tell you how to salvage it, and I'll tell you kind of how to deal with this in general so you don't actually have to worry, I think, too much. If you just kind of do something from the beginning, I'll show you in a minute. There's some way to do it, to approach this so that you don't really have to worry about making the inequality go the right way. Okay, so here's the new principle. This one right here, I love this. Multiplied constants do not affect convergence or divergence. So like, it's kind of a silly point, but just think about it. If we start, with this integral, we know this converges, p test b equals 2. If I multiply by 100, right, I can pull this 100 out in front. This is the same thing as 100 times the integral from 1 to infinity of 1 over x squared dx. And so the fact that the integral is finite, if you multiply by 100, it's still finite. And then, but you could also multiply by 1 over 100, say, if I want to multiply by 1 over 100, that would also be fine. Doesn't change anything. So it's kind of nice. Like, you have the integral, you can just sort of like throw in constants willy-nilly and you're fine. It doesn't change convergence. That's what this principle up here is saying. That's what I'm saying. Okay. Yeah, and so then I say, okay, so we started with this bad inequality, x squared minus 1 is less than x squared, but I claim we can use multiplied constants to make the inequality go the other way, the more helpful way. And in fact, if I even just put a 1/2 in front of x squared, I claim the inequality is sort of the x, it's on the other side of x squared minus 1 now. And you can check the graphs. In fact, let me see if I can do this. Oh, you get to see me for a second. Hi guys. Let me share a different screen with you. Oh my God, can I find the right thing to share? Okay, this one right here, I think is what I want to share. Yeah, so I actually plotted, remember, I love using the Google search bar for this stuff. I plotted x squared, I plotted 1/2 x squared, and I plotted x squared minus 1. And if you do that, let's see. So x squared and x squared minus 1 are actually very close together, the blue and the yellow, or gold, or whatever color that is. They're very close together. But x squared, again, is bigger than x squared minus 1, which is not what we wanted, right? On the other hand, if I multiply x squared by 1/2, it sort of flattens out. Now you get this red graph. It's sort of flattened out, right? And, if we zoom out, we can sort of tell, oh yeah, like the red graph's always below the yellow graph. Red graph is always below the yellow graph. Well, past a certain point. So past 1 point, whatever this is, 1.4, something like that. And so really we care about from 2 on. So this holds from 1.4 on, so we're fine. So in fact, that's what I said. If I go back, let me go back to my iPad screen. Is it back? Okay. I go back to my iPad. What is going on here? Why is this? Sorry. That's where this inequality right here came from. Let me just, right? I sort of said, I checked this visually, just looking at the graphs. And so if we start with this inequality, now again, it's going the good way, it's going the right way. Now if we flip everything over, right, the inequality reverses again. Now you've got a 2 on top because the 2 was on the bottom before, now it's on top. So you flip that over, and then you flip the x squared minus 1 over, you get 1 over x squared minus 1. And again, then we sort of integrate both sides. From 2 to b, that still holds. We take the limit as b goes to infinity, and those are become the improper integrals. And now we have this inequality right here. And this is finite because, again, the 2 can pull outside. And so this is also finite. because it's less, Good. Okay, so that's kind of a nice trick maybe, or just a principle that like, not really like tricks, but it's a principle that you can sort of actually use multiplied constants. They don't affect convergence, but they can affect inequalities. I guess that's the way to say it. Okay, and then just to give you this sort of like the overall, like I say, the safest way to do any of these, you could just overkill and bound on both sides, and then you don't have to worry about anything. You know, you can just like, I'm just gonna pick 1 over 100 and 100. Like I bet x squared minus 1 is between 1/100th of x squared and 100x squared. Again, we can go to the graphs. Oh, I can share without going back to have you look at me, which I like. I don't know why I like that. I can switch the window without going back to my camera. Okay, so here is plotting those three functions. So 1 over 100x squared, x squared minus 1 is now, sorry, I don't have the color scheme the same, x squared minus 1 is now red, 100x squared is yellow, 1 over 100x squared is blue. And now, you know, there's some weirdness going on here near the origin, but if you zoom out, like clearly the red is in between, is above the blue. This maybe, no, that's not the way, this way. Yeah, the red is above the blue and below the yellow. You really can't even see the yellow. It goes way off the screen. And so this is my claim that by using these constants, the 1/100th sort of depresses the graph a lot, sort of pushes it down. And then the 100 makes the graph just, I can't, the dot goes off the screen immediately as soon as I move the mouse left and right. So it goes up really fast. And so the red graph is just this x squared. It just kind of stays in between. And so you can see that there. And again, it's also true for, yeah, I mean, it's true as soon as x is bigger than 1, in fact, or around 1. Okay, great. So, I don't know how I change. Oh yeah, okay. So let me change back to the iPad again. First time, guys, bear with me. Hopefully this will become more smooth. All right, iPad. Where are you? There you are. Okay. So, so yeah, so we get this these inequalities here that we just sort of checked visually, right? And then if you go through all the same steps, you sort of, you know, flip everything over, integrate both sides. I don't want to do it all. You should probably do it yourself. But these kind of steps that we did up here, where you flip, we flipped first, we flipped, then we integrated both sides, then we took the limit, then we just rewrote the limit as the improper integral. And if you do all those steps here, you'll end up with something like this final inequality right here. And now this is really cool. I like this because I didn't have to worry about, like, you know, being on the right side of the inequality, because if you think about it, let's look at this. This one is this right, change colors. This is finite. This is finite, it's the same integral, is also finite. And this is stuck in between. So it's between two things that are finite, so it is also finite. And that's an argument that the integral converges. And that way you don't have to worry about putting the inequality on the right side. You know, you do it, if you do it on the wrong side, you go all the way to the end and you get the wrong inequality, not the one you wanted. So again, that's why I really like this approach of just the overkill and bound on both sides. Just pick a big constants. It's kind of a nice idea. Okay, guys.